Okay. Let me turn off the heater so you don't know what's going on. So to recap where we were on Friday, we talked a bit about fit measures and fit statistics for the model, particularly about the RMSEA and the standardized root mean square residual. There are some older fit statistics that you'll frequently see in models, and those would be taking the chi-square and dividing it by its degrees of freedom, and that gives you kind of an idea about how far away from the number one you are, because if the null hypothesis is true, the mean of the chi-square is equal to its degrees of freedom. So let me tell you a little bit about the history of fit statistics. It used to be that people just used the chi-square statistics. So the early papers that Uriskog and others put out just fit a model and reported the chi-square. And not surprisingly, maybe, especially given that Uriskog was at that time working for ETS, the chi-squares were always significant. And as a result, they would make some little twiddles to the model. They would look at the observed and the expected variance covariance matrices, and they would add a path here and there to improve model fit. And the net result is you had these diagrams which were extremely ornate, that didn't really make a lot of sense, that were adjusted on the basis of post hoc things. You know, these days we would call that p-hacking. And as a result, the area very slowly moved toward trying to think of ways to overcome this fact that we seem to have chi-squares that are really large. And the first avenue that people looked at was to capitalize on the chance, on the observation, that chi-square difference tests exist. So as we talked about in playing with Onyx, you can draw one diagram that will have all of the paths in it, and then draw another diagram that has one of the paths fixed to 0, that is, the path really isn't there, and look at the chi-square difference between those two things. And if the chi-square difference is not significant, the more restricted model, the more parsimonious model is adopted. And if the chi-square is significant, the more complex model is adopted. The rationale was, more generally, if you're fitting things, well, I could have a more complex model and a simple model. Perhaps both standalone chi-squares are significant. But the reason that those things are significant is due to other model violations of the data, specifically the conditional normality assumption. And the violation of the conditional normality assumption, for example, is going to be the same across your two models. So the chi-square difference is going to be not affected by that non-centrality parameter in those two models. And I walk you through an example here. You might want to think about one model where there's no correlation between the measurement errors and another model where there is. You calculate those two chi-squares, and the difference between those two numbers, in this case 107 versus 96, is going to give me, for the correlated two-factor model, a chi-square difference of 107.70 minus 96.64 is equal to 1106. And this is distributed with degrees of freedom equal to the difference in the degrees of freedom between these two models. 5 minus 4 is 1. And that's highly significant. So we would take that as evidence that a correlated factor model is better than a single factor model. And that's a way of doing this type of thing. One way of handling this is also to think about cases where models might be nested. And one of the things that is important to mention at this point, two models are nested if I can get from one model to another by adding paths or subtracting paths or constraining values. So for example, in the example that we did before with Onyx, a 2 predictor model with 2 regression weights estimated and another model with only 1 regression weight estimated is nested because I can get from one model to another by erasing one of those arrows. It gets a little bit interesting if you're looking at testing whether there's one factor present versus there being 2 factors present that are simply correlated. And the way that we can think of those things as being nested is to say, well, under a more restrictive model, the 1 factor model, I'm going to constrain those 2 factors to have correlation 1. And under the correlated factor model, I'm going to say, well, actually, there's a covariance or correlation between those 2 factors. So nesting does not only involve zeroing out things, you can also constrain correlations to be 1 and then free them. The objective here is we're making a model more complex by having more free parameters in it. So a correlated factor model is more complex than a single factor model because in a single factor model, I'm constraining that correlation to be 1. Generally speaking, if you're doing your project, dissertation, thesis, and you can do model comparisons that are nested, life is a bit easier for you because power is better, it's a cleaner interpretation. If you can think of ways that people in your research area think about the data that are arranged in terms of their complexity. Model comparison is a little easier to do than standalone model evaluation. So that got people to thinking, well, how might I go about judging whether my model, which has some arrows and correlations in it, how might that be different than a baseline model? That is there a model out there that is somehow simpler than any other model I might draw? Well, one thing that you can do, one model you could begin with, is the thought that all of my variables have variances and there are no covariances in the model because any model I draw on top of that will be adding arrows to it. This is known as the independence null hypothesis. In terms of a path diagram, this is what it looks like. I'm saying once upon a time, there were 5 variables. They all had freely estimated variances and no covariances. And so when you're looking at a printout and you see the chi-square for the independence model, this is what the computer program is doing. Now, it's pretty weak tea that, this as a very parsimonious model is probably going to be rejected in any data set that you have. It is possible for you to test a chi-square statistic relative to that independence model. So if I'm doing the independence null, I have 5 variables here. Well, how many variances and covariances do I have? 6 times 5 is 30, divided by 2 is 15. I'm estimating 10 variances. So the independence null model, I'm estimating 5 variances. So the independence model has 10 degrees of freedom associated with it. And its RMSEA is really bad. Now, if we go back to our other model, that model fit appreciably better, but you can calculate the chi-square difference between that model and the independence model as follows. 10 minus 4 gives me 6 degrees of freedom for that chi-square. That gives me a huge number minus a very small number, which gives me a really huge number here, all with 6 degrees of freedom. And that is a possibility. But as I said before, who in their right mind believes that all of the variables that you chose to look at were absolutely unrelated to each other? But this idea of the independence model is a base model for the fit indices that we're going to be talking about. Let's see, I've got to fix something on page 178. There's a Y there that shouldn't be, okay? So in terms of our geography, we're going to be talking about 3 things now. There's type 1 fit functions, type 2 fit functions, and there will be information criteria. And a review of these will be the object of our discussion. In terms of where we stand these days, to give you the bottom line, when you write up your paper, you'll report the chi-square and its degrees of freedom, and at least significant probably, and you're doing that because other people might use that chi-square to calculate their own fit indices. Second, you'll probably report the RMSEA. Third, you'll probably report the TLI, or also known as the non-norm fit index. And there are some who would argue that we also include the CFI, comparative fit index. If your models are not nested, the only thing that we can do is to talk about information criteria that we'll talk about below. When you look at an SEM program, you'll see a lot of fit measures. And so I'm surveying those for you and giving you an idea of their general rationale. The 2 types of fit indices that we have follow this little format. A type 1 fit index looks at some measure of fit for a more complex model minus some measure of fit for a base model or a simpler model. And we're going to divide that by whichever is larger. A type 2 fit index is going to take as its value in the numerator the same thing, but the divisor is different. We have our fit index for our simpler model minus the expectation for the fit index if the model is true. This is if the model is true for the target model. And that's really kind of a nice insight that when you look at computer printouts with SEM programs, there's a whole bunch of them, and this is a way that you can understand several of them. One of the most popular indices, and the one that seems to work fairly well in Monte Carlo studies, is the TLI, the Tucker-Lewis index. And I've told you before, I have kind of a long distance across the years man crush for Ledger Tucker, because he was just known for doing an awful lot of very clever things. And the TLI has the following form. I'm going to take the chi-square for the base model and divide it by its chi-square. So notice what's going on here is that idea of taking a chi-square and dividing it by its degrees of freedom that I talked about at the beginning when we introduced the chi-square. And we're going to subtract from that the chi-square for the target model divided by its degrees of freedom. And that's all divided by the chi-square for the base model, this one, minus 1. And it's a type 2 fit measure. The reason we have the number 1 here is the expected value of a variable from a chi-square distribution is its degrees of freedom. So if, for example, the target model is true and its degrees of freedom are the right degrees of freedom, I ought to see the number 1 here. Now, if you're interested, the TLI is based on kind of the idea of a reliability index from analysis of variance. But it's important to remember that the NNFI is not a computational formula for an interclass correlation. It's only an estimate, and even that's kind of an analogy. A couple of things to know about the TLI. It can take on values. I mean, although it's kind of supposed to, expected to be on the range 0 to 1, with 1 indicating really great fit and 0 indicating awful fit, it's only an estimate of that range. So you can observe values that are negative, and you can also observe values that are bigger than 1. Sometimes you'll read articles and people will say, oh, the TLI was 0.9. That means 90% of my model fits. And it doesn't. It's just a number that goes from 0 to 1. There's the Marshall and McDonald Psych-Bull article is a really, really huge Monte Carlo study. And they found that of the fit measures that are out there, generally speaking, type 2 fit measures perform better than type 1. And of the type 2 measures, the TLI or NNFI seems to be the least affected by sample size. It does have a larger variance in sampling studies. And Roderick McDonald and Peter Bentler went around and around about the TLI's advantages and disadvantages. And Peter Bentler wanted to, at that point, advance the norm fit index, which can never go beyond 0 and 1. But McDonald said, well, but in Monte Carlo studies, the non-norm fit index works better. At which point, McDonald published an article that said, okay, we'll do a modification of the TLI. If we estimate the TLI to be 1.1, we're just going to call it 1. And so that's the reason that the modification doesn't appear in a printout, is it's just kind of understood. You could just call it the number 1. Well, so I've got this thing that goes from 0 to 1. And how should I interpret it? So if you go out to articles, like Peter Bentler would say, you'll need a TLI, or Roderick McDonald, a TLI of at least 0.95 to indicate good model fit. But it depends a lot on what kinds of questions you're asking and how internally consistent they are. So Bentler and McDonald and Beck-Mutane, they're all doing work in addictions. And reports of behaviors of problem use are pretty reliable things, mainly because we kind of ask overlapping questions often. And your report of how much alcohol, say, you've drunk in the past 2 weeks is pretty strongly related to how much alcohol you've drunk in the past month. And other areas, like I think I worked on a mindfulness program, a mindfulness article a couple of years ago. Well, that's a lot more complex, how people meditate, how they relax, and so forth. So you can't really expect to see exactly 0.95 TLIs. So generally speaking, you're going to want to see something in excess of 0.90. And above 0.95 is something you'll hear reviewers talk about. And even another little caution on that is it also depends a bit on how your study is designed. So if you're doing a study where, say, your predictor variables are designed to be uncorrelated, so say you did a study where you looked at an equal number of men and women and an equal number of young, middle-aged, and old people, it's a balanced design, you're not going to get a TLI that's going to be really high, because by design, an awful lot of the variables in your study have zero correlation. That is, for a subset, a submatrix of your variance covariance matrix, the independence model is true because you did it by design. So we can't just religiously interpret the TLI as you're above or below this magical number. Often in smaller studies, larger numbers of variables, constructs that have loadings that, say around 0.5, 0.6, you probably will be seeing TLIs around 0.9. And if you're looking at really, really reliable things, you're going to see TLI values of 0.95, and that generally gets you past things. How can you fix that? Well, you can make your model more complex, which is what everyone is doing. You can also go back, as we mentioned before in earlier chapters, and look at influence diagnostics, and removing influential observations will frequently also improve your TLI a lot. Okay. Awful quiet this morning. Usually I get interrupted at this point. Any questions? All right, well, the norm fit index is beloved by some people because it goes on the range 0 to 1. And the formula for it is the chi-square for my base model minus the chi-square for my target model divided by the chi-square for my base model. So notice the degrees of freedom are kind of gone. It's scaled a little bit due to the estimated non-centrality parameter. And that gave birth to the CFI. And the CFI is, in terms of the non-centrality parameters, is this formula, the base minus the target divided by the base. And because this delta is equal to the chi-square minus its degrees of freedom, this is another formula you can use for it. Now, in terms of who wins, generally speaking, the norm fit index gets cited a lot out of tradition. As pointed out by Mulaic, the CFI is bounded between 0 and 1, and it also seems to have smaller bias. And it's a lot smaller if you have a small sample, kind of negligible to moderate and large sample sizes. And if the CFI is less than 1, it is always going to be less than your TLI. And generally speaking, your numbers here are 0.90 and 0.95. Third part is our information theoretic values. Sometimes our models are not nested. That is, I can't go from one model to another by adding or subtracting arrows or constraining parameters. And in those cases, the tools at hand are information criteria. Now, to cut to the chase, there's not going to be a magic number cutoff for information criteria the way there are for the TLI or the CFI. And this is because the number that you're going to get out with an information criteria is unique to your study. It's going to change based on how many variables you have in the study and how many parameters. So if I do a small study with, say, only 4 or 5 variables, my AICs are going to be a lot different by definition than if I have 20 variables in my study. Information criteria values come to us from the field of economics. And in the field of economics, they generate a whole bunch of models. And they are really not that interested in doing a statistical test of whether one model is appreciably different than another. They just want to know which model wins. So the way you proceed, if you're looking at AICs, is you run your candidate models and you say, this is the best one, I'm done. AIC values generally run off of the log likelihood function. And they incorporate a penalty for model complexity, specifically how many parameters you estimate in the model. One of the first variants proposed was by a Japanese professor by the name of Akaike. And he was kind of like many people I admire in academia, a very humble person. The formula that he proposes here is to take -2 times the log likelihood, and then -2p, where p is how many parameters you have in your model. And as I mentioned before, it's idiosyncratic to your model. You just select the model with the smallest AIC value. So models that have an awful lot of parameters get a penalty. And if you have very, very few parameters and roughly the same log likelihood value, you're winning. Now, one of the problems with the AIC is that you really have to go back and look at your software to know if a small number of the AIC is good or if the large number of the AIC is good. Because, for example, M plus uses this formula. And it can only take on positive values. I think that's the advantage. There's another formula out there, which is the chi-square plus k times k plus 1 minus 2 degrees of freedom. And it has the advantage that it's based on the model chi-square rather than the likelihood function. And if a model is completely saturated, has 0 degrees of freedom, AIC is going to turn out to be how many parameters times how many parameters plus 1. But my take-home message for you is, on AICs, look at your computer program and check the manual to see if large numbers are good or small numbers are good. Second, the Bayesian information criteria, the BIC. This has also got penalties for the number of parameters in the model, but it also has a penalty. That penalty also involves the sample size. And it's an old one from 1978, and this is the formula for it. It's the chi-square for your model plus p, the number of parameters, times the natural log of the sample size. And the BIC in Monte Carlo studies generally tends to perform a little bit better than the AIC. I mean, they're kind of sort of the same bits of information. But, the penalty function of the BIC will tend to prefer models with larger numbers of parameters as your sample size gets bigger, as you get larger n's. And as I mentioned, it seems to work a little bit better in discriminating between models. How well either the BIC or AIC is going to work depends a little bit on the kind of models that you're looking at. So if it's the case that you actually have the true model, that is, the process that generated the data among the alternatives being considered, the AIC could lead you a little bit astray. However, if the true model is not among them, the AIC seems a little bit more efficient than the BIC. It seems to asymptotically give you the model that minimizes the mean square error. And both of those observations are asymptotic, that is, as sample size goes to infinity. But they are kind of some comments about whether it's going to work well for you in practice. The last information index is called the Bayes factor. Now, you will not see this in your standalone printouts. The Bayes factor is something that you will have to calculate yourself. And to be frank, the Bayes factor is probably something that you would want to consider more if you would make the leap to use Bayesian information, Bayesian estimation, which we talk about in advanced SCM more. But I present it here for completeness. The Bayes factor is, generally speaking, the probability that your data occurred given model 1 divided by the probability that your data occurred given model 2. And again, doing a little bit of math here, you can calculate that probability of a given model as the probability that your given parameters happen given model 1 times the probability of your data given the parameters in the model. It's this little bit in here is an application of Bayes' theorem. And as a result, if you're comparing these probabilities, you'll end up with a number that will indicate how much better one model is than another. And Cass and Rafferty in 95 gave us this little table for interpreting how much better one model is than another. So if you've got something bigger than 150, you have very strong evidence that one model is preferable to another. If you've got a number between 1 and 3, the models are more or less equivalent. And 3 to 20 is positive, and 20 to 150 is strong. Now, as I mentioned, if you did Bayesian SEM, you'll be able to get these probabilities out, and you can calculate that Bayes factor. In terms of the printouts that we have from Levon or Amos or M+, we don't. But Cass and Wasserman had this approximation to the Bayes factor. E to the minus 0.5 of the BIC for the more complex model divided by E to the minus 0.5, the BIC value for the null model. And I've had people in previous years, I showed them this formula and they calculated the Bayes factor inside of Excel. And they'd come to me and say, well, it doesn't work. Well, the reason it doesn't work is these numbers, these BICs, are generally speaking large values. So you're outside the mathematical precision of what Excel does when you say, let's take E to the, maybe 1,000 times minus 0.5. I mean, it just goes outside the rounding error of the machine. So one way to handle this is to first take the natural logarithm. If it's the natural logarithm of E to something is this term. And dividing with natural logarithms is subtracting. So if that's the case, the logarithm of the Bayes factor is 0.5 times BIC for HO minus 0.5 times the BIC for H1. Take this number and then exponentiate it. Take E to this, and that gives you the Bayes factor. Right? So that covers everything you need to know about looking at fit statistics, the most commonly used fit statistics in SEM in terms of your printout. Any questions or comments? Okay, well, let's take a look at power. When you're proposing a grant, when you're telling your committee you want to do a master's thesis or dissertation, they're going to want to know, are you going to have power? I mean, are you going to be collecting enough participants to find the effect you anticipate? Conversely, and this is something people kind of forget when they propose to a granting agency, are you asking for an appropriate amount of resources? This is one of the frustrations, across the 30 years of doing grants that I have with granting agencies, that if you calculate your power study and you say the power of my study is 0.99, the response of reviewers is, oh, well, obviously you don't need all those people. We'll fund your study for about half. Well, everybody around the table knows this happens. So this kind of results in the people writing the grant conducting just so studies that will say, here's my power analysis, and everything just magically happens to be around power of 0.8, 0.85. And sometimes, even though the power for the whole model is 0.99, you can say, well, we actually want to be sure to have enough women or minorities or other underserved populations that we have sufficient power for those groups. So one way to do power is to compare nested models and to try to work with what's going to be the power for my study, comparing a more complex model to a simpler model. And to again give the landscape of this, this is a model that works well for looking at power for testing models that differ with only a few parameters. The second approach that we talk about later is monocolor power studies for all of your parameters simultaneously, doing some generation of many, many replications of a study. If you're looking at this first technique, when our tasks are to generate a predicted variance covariance model for our more complex and our simpler model. So our first step is to generate a covariance matrix under the alternate hypothesis. So there's the simpler model. And you'll have to put in some numbers here. So for example, if we wanted to test the power of an SEM to detect a correlated two-factor solution instead of a single-factor solution, we could say, let's take a look at a path diagram with factor loadings equal to 0.7 for all 5 variables, and error variance is equal to 1.7 squared. In other words, that's going to be giving me manifest variables that will have variance 1. And maybe the other model, rather than a single factor model, is to say, well, the correlation between the two factors is 0.8. So I'm going to use that predicted covariance matrix associated with a simpler model to find the non-centrality model. So in this case, I've got 0.8 as my correlation between the two factors, all of these loadings, and I'm going to fit the single factor model to the data. That chi-square is going to give me minus its degrees of freedom is going to be the non-centrality parameter. So for the example given here, if I had a sample size of 100, the non-centrality parameter from the SEM program is 4.964. So I make my variance covariance matrix based on the more complex model. I fit the single factor model to it. I say, hey, there's going to be 100 people in this, and that gives me my non-centrality parameter. This non-centrality parameter associated with the chi-square with 1 degree of freedom, because I'm testing a correlation, gives me that value. All right, so the next thing I do is to find the critical chi-square value for that analysis. So inside of R, for example, I'm going to say, give me the chi-square distribution value for p equals 0.05 for 1 degree of freedom. Or if you're playing with Excel, here's the formula I need to find for the inverse of that. If you're using SAS, this is my little formula call. So the critical value for a single degree of freedom chi-square at 0.05 is 3.84. And now, given that 3.84, I'm going to come back and find the non-centrality parameter in step 2 and the degrees of freedom associated with the base model. I find the probability of rejecting the base model. So graphically, what we're doing is we're saying, for a 1 degree of freedom test, this is what the chi-square for a 1 degree of freedom looks like. This is the critical value. If I have 100 people, this gives me my chi-square value. Everything associated with the value that's larger than the 0.05 level for this chi-square is power. And I put 2 scenarios in here. If I have 100 people, I've got 61% of the area under the curve over here. If I have 200 people, I have 88% over here. And I give you the code inside of R if you want to make that picture. So when does this come in when you're doing grants? Often, if there is a particular parameter that you're really, really interested in, most often this happens in behavior genetics. I'm interested in looking at finding a genetic correlation above a certain amount. or if I'm interested in looking at a particular outcome, if I really want to know who at the end of the day is going to graduate from college or not, and I'm just interested in that question, this is the way you would set up power for that one parameter. Often, there's just all kinds of factors at work that affect power. So, generally speaking, what's happened over the course of time is reviewers would be looking at these single parameter power things and say, well, this is all good and fine. If you have, say, 200 people, that's a nice power thing. But in reality, there might be missing data. Maybe 30% of your data will be missing. Wouldn't that decrease the power? And often, your structural equation model is very complex with many loadings, many parameters that are of interest. And you want to be able to say, what is the power for all of the parameters in my model? Well, if you did this approach for everything, you'd be pretty weary by the time you were done. So an easier, nicer way of doing this is to do what is called Monte Carlo simulation. And probably the best package for you to be doing that is M+. There is a module inside of R that's also available, but it doesn't have all the options that M+ has. Well, what's a Monte Carlo approach? What I'm going to do is to specify my true model for the data, the model I want to win, the more complex model. And we're going to use various values from that true model to simulate an awful lot of data sets. And based on that, I can then look at raw power, the proportion of times that a given loading was found to be statistically significant. And you can put all kinds of nice little twiddles on that inside of M+. I can say, maybe 30% of my data are missing. Or I can say, well, you know what? Men are different than women. I think that the men are not going to show up to my study, say 40% of the time, and the women will show up maybe 80% of the time. And you can then look at how that starts to affect power. You can also fit the base model, a simpler model, and explore how many times that base model resulted in a chi-square that was significant. And I give you, in the reference section, there's a very nice, walks you through several examples of doing this in 2002. But I thought it would be kind of helpful to do one here as well. So here's what the code looks like. And I can see I'm probably going to be here at about the end of the class. M+ is a line-by-line program. And when you want to use the Monte Carlo module, you put in that, hey, Monte Carlo means I want to investigate an unreal scenario here. It's not real data. And we start by saying, what are the names of the variables I want to do in my simulation? And how many observations are going to be present in the data set? N reps is how many times I want to replicate my data set. 1,000 is usually good enough. And the seed is some random number. Generally speaking, for technical reasons that are outside of this, it probably should be an odd number, and probably 5 digits is nice. And what comes down here are our values for the true model. So in the population, I'm going to say all 5 variables have a starting value mean of 0. And factor 1 has a starting loading of 0.7 for the first variable and 0.7 for the second variable. Factor 2 has 0.7s for variables 3, 4, and 5. The variance of factor 1 and the variance of factor 2 are fixed at 1. And the correlation, covariance, between factor 1 and factor 2 is 0.8. The error variances down here are 0.51. How did I get 0.51? Well, that's 1 minus 0.7 squared. And then down here, I'm going to say fit the following model to that randomly generated data. So in this case, I'm going to fit the wrong model. I'm going to fit all 5 variables loading on one factor, and then hit the run button. And if we wanted, we could also do the 2-factor model by saying there's 2 factors here. I could copy this section down here and paste it in up here, and that would be the true model. And I can then save those chi-squares and calculate the difference score. In terms of running the model once, this is, part of the printout that happens. And we'll get as far as we can today, and then we'll talk more about what it means. So here are our 5 variables, and these are the loadings for them. And the population value is 0.7. That's the true value. Average is the average loading that was estimated across all of the 1,000 times I replicated the study. The standard deviation is the standard deviation of the loadings across all 1,000 variables. Well, this standard deviation is kind of the same thing, the same idea as what the standard error of the loading is. So over here, here's the loading, the standard error that was estimated in the data. So these 2 numbers ought to be fairly close to each other. And if you're finding a larger standard deviation here, that tells you that the standard error estimate is probably a bit smaller than it ought to be. The mean square error is the mean square error across all my replications. Coverage is interesting because this is the proportion of times that the estimated parameter, the confidence interval from a given replication contained the true value. So in one study, I might, for example, have 0.61 as my value. And it has a confidence interval on it. Well, if that confidence interval included 0.7, then that's going to count toward my coverage. So out of this study, 74% of the time, the confidence interval included the true value. And the last number over here is the proportion of times that that loading was judged to be statistically significant. So this is power. So in this study, for these loadings, for this sample size, my power was 1. And we can also calculate the bias. So in this model, we misspecified the model. This 0.61 is different than 0.7. And I can apply the following formula to get the percent error associated with that model. Well, I've been talking, you've all been pretty quiet, but let's continue on the rest of this today. I did want to tell you, for some odd reason, Adobe Premiere is no longer letting me edit the videos, so I've been uploading the class material to the YouTube channel. So visit there, and you should be able to pick up all of the classroom lectures. It's just that I haven't zoomed in and zoomed out of diagrams, and I haven't cut out the awkward pauses that happen during classroom. Okay, any questions?